Okay, welcome to lecture 9.1, Neural Implicits and Point-Based Clothing Models, part 2. So we covered part 1 already. This is going to be part 2. Okay, so in part 1, we've seen like how to use neural implicit models for general objects, and now we're going to see how to make these models specific to work specifically well for humans. So PART works in like modeling people, in particular modeling people in clothing. As we've seen, they are mostly based on meshes, which are convenient for some aspects, but as we saw, they have problems with modeling topology and very complex clothing. So the topology needs to be manually defined, and they are limited in resolution as well, right? And we were seeing, if you recall, this comparison of parametric meshes versus implicit functions, and we saw that implicit functions or implicit surfaces, they seem to be convenient for topology changes, and they are also more amenable for learning because they allow you to predict, to make predictions per point. Okay, so basically models, neural implicit models for people in clothing and for articulation, they are high fidelity and they are flexible in topology, and they allow some degree of control, although this is more difficult. And very importantly, they can be learned directly from scans without registration. This means that the output also does not produce meshes that are registered. However, it's sometimes convenient to not worry about registering the data beforehand. All right, so basically, like the vertex-based human models were a function that was mapping from pose and shape parameters to the 3n vertices of a model. Actually, this should be 3n, or I mean, depends on how you define it. Like, so here V represents a vertex, so that's why this is 3-dimensional. And this you would have for every vertex in the model. And in neural implicit models, you have instead that given a latent code, which is dimension D, and a point P, which is 3-dimensional, it predicts a distance or an occupancy, which is a scalar, right? So that's kind of the mathematical difference between these two models. And now if we want to make these neural implicit models more human-like, like a human model, we have to make them dependent not on a random latent code, but on latent codes that are meaningful. And in this case would be the shape, the pose, and the shape of the human. And again, we want to predict this distance or occupancy. So the first model really that that attempted to predict like the human surface or an articulated surface with a neural implicit model was NASA. And so basically here, basically the argument in this paper was that you need to reason a little bit about this articulated structures. Otherwise, it's going to be very difficult for the network to learn for every possible pose what is the occupancy of the surface, right? And to illustrate this, basically they show here in this work, basically it's shown here like the naive solution, which would be some representation of pose. In this NASA paper, the representation of pose is a little bit strange. It's basically taking the rigid parts of the body and taking the root location and then basically applying the inverse transformation. It doesn't really matter at this point. It's just a way of getting numbers that encode the pose. And it was decided at that point that this is like more convenient for the network to understand the pose than the joint angles. But that's not the important part. The important part is that if you go from pose directly to this implicit surface, it's going to be very difficult because you need to learn for every possible pose what actually the configuration is, and that's very difficult for a network to learn. However, we know that the human body is articulated, and so the question is like, how can we incorporate a little bit more of prior knowledge here, so that the network has like an easier job to learn this task. So remember that this is the simple model, which was deforming in the canonical space. And basically, after deforming the canonical space, it applies the articulation to get this vertex. Now, the question is, like, can we extend these concepts to the neural implicit models? And the answer will be yes, and you will see how. All right, so the first thing that we can do to improve this unstructured model, which is the naive solution, which does not generalize to new poses, is to incorporate what is called like a piecewise rigid model. So what this model is going to do is, like, for every point in the pose space, it's going to unpose it according to each of the parts. So we don't know for a point in space to which part this point belongs. We don't know. But what the model will do is, like, assume that it belongs to each of the parts, unpose the point according to each of the parts, and then take the occupancy as the maximum. So predict the occupancy for every rigid part, and then the occupancy of the point will be the maximum occupancy. What does the maximum mean here? It means that a point is occupied if it's occupied by any of the parts, right? So if any of the parts outputs a 1, which is a 1 occupancy, or close to or bigger than the threshold, then the network here, the total result of the max will be that the point is occupied. So basically, this makes a lot of sense, right? And this is how we saw before how to combine like implicit surfaces. We saw that it's easy to compose them by these max operations in order to obtain the union of multiple parts. So this is what we will do. I repeat, you start with a point in the post space, you transform it to the canonical space with these inverse matrices, B0 until BB. These are the absolute transformation matrices for every part. And then, like, you have a network that predicts in this canonic space the occupancy. Again, this is a recurrent theme that you will see, that predicting things in canonic space make things easier because it's more repeatable. It's always in the same places. The points always land in similar places, and you don't need to learn for every possible pose what the occupancy is. So this improves the results significantly, and you can see here, this is the rigid part model, which can already reconstruct, like, the poses much better. However, like, similarly as with simple, when we model this rigid, the mesh with rigid parts, like, you have problems at the intersections because the human body is not a collection of rigid parts, but it has non-rigid deformations as well. So basically, like, in order to model these pose-dependent deformations, similar to the pose-plane shapes here, what it's done is, like, you have like a function. These occupancy networks are a function also of the pose. So this way, the network in canonic space can learn occupancies which are dependent also on the pose. So the pose here, theta, is, you know, conditioning this function, which is the occupancy for each of the parts. Right, and this is completely analogous to these pose-plane shapes. The only thing that the pose-plane shapes were is vertex displacements. Here, this is like theta, which conditions a full network. And you can see that the deformable model, in particular at the elbows, if you can see here, it produces much smoother results as one can expect. All right. One problem of NASA was that it needs to invert, it needs to map the points back to the canonic space, and basically it had part-based artifacts, and it had a limited ability to generalize to new poses. So this low-dimensional pose encoding does not fully remove these long-range spurious correlations. And so when the poses are very far away from the training distribution, then this model will fail. So this is addressed in this work, which is called COPE. And the idea is quite straightforward, but it makes a lot of sense. So basically, you want to obtain the implicit surface of the simple model. And essentially here, what you will do is, like, pose the simple mesh, consider the parts separately, and then, like, canonicalize these parts independently. and then run PointNet here to predict like latent codes. And from these latent codes, we're going to predict these occupancies. So similarly as before, but the main difference is that now the networks can see, the local structures of these unposed parts in the canonic space. And so these latent codes here, Z1 to Zk, are much more powerful. But this idea of unposing the points according to the rigid parts, in this case, they are denoted as G1 to Gk, still remains. So this is the same as NASA, and the max is still the same as before. The main difference is these latent codes that now have information about how the local pose looks like in the canonic space. And yeah, so you have per part body part plus few points from neighboring parts, and then you have like this shared occupancy. So as a result, like COPE has much better generalization than a model like NASA, right? However, like these part-based models, they always have like these problems at the intersection. So the COPE is no exception. And basically also COPE cannot model clothing or fine-grained details. It's more like an articulated model. Now you might ask, why do you need to learn like a model that is implicit? Well, for example, like having the implicit surface representation is useful to, for example, test whether a point is inside or outside, which is useful for intersections, to know, for example, if clothing is inside or outside the body in simulation, or to know, for example, like whether the person is intersecting a 3D scene or not. Right, so part-based models, yeah, in general, like you need the skinning weights for the part decomposition, and part artifacts are prominent, in particular for out-of distribution poses, and cannot model clothing, in particular loose clothing. All right, so how do we model these fine-grained deformations? And this is the next topic. So basically, I'm going to describe now a paper that is called Neural GIF, which we published at ICCB 21, which is basically learning pose and shape conditioned neural implicits using learned LBS and a canonical shape. And so you will see that it's interesting because it's completely analogous to the simple model. But while the simple model starts with the canonic space and applies a series of deformations to get to the pose space, this works in backward mode. So basically, it starts from the pose space and it will apply a series of transformations in order to evaluate the occupancy in the canonic space. So how this works, you start with a point in the post space, and then you unpose it. We will see how to do this. Like the network needs to predict the skinning weights to do that. And then we're going to predict like these displacement fields, which is the same as the pose-blind shapes, but now they are going to be a continuous function of every point in space and the pose and the shape. And these displacements, you will see that they are inverse. So if you want to make the surface grow, like these displacements will go in the opposite direction. And you will understand in a second why that's the case. Right. So the question is like, how do we map a query point from the pose space to the canonical space? Right. So this is the work, which is called Neural GIF, and the name stands for Neural Generalized Implicit Functions for Animating People in Clothing. So first, at a higher level, like the main goal here was to train directly from scans and to obtain like a neural implicit surface, which could be posed with a skeleton pose. So the input would be a skeleton pose and the output would be the neural surface, including all the clothing details. So this model is not generalizing across subjects. It's a subject-specific model, but it can produce this level of fine-grained details. So to solve this problem, like we build on like ideas that were known or presented in computer graphics as back as the 91. So basically, like, the key challenge we have here is like, how do we apply deformations to an implicit function? And so this can be easily done because, like, if you want to apply a rotation and a translation to an implicit surface, what you can do is like, basically what you need to know is like the occupancy or the distance field in these post new locations, P prime. So in order to know the occupancy of this point, for example, what I can do is invert the transformation, consider R minus 1 and subtracting T from P prime in order to go back to the canonic space and check what the occupancy is. I can always do that. I can invert, and I can have here like this space as being my lookup table, right? So I basically like always invert and lookup. And this is what mathematically is written here. The surface S prime after the transformation is nothing else than the points P prime, such that f of R minus 1 of P prime minus T, so the inverse of P prime, bringing it to the canonic space, equals this threshold function. And this is not only for rigid transformations, but it's for more generic deformation fields like D of X, Y, Z. You can have a deformation field that deforms every point P in this canonic space into the post space P prime, and you basically would just, oh, this formula is missing here. You would just apply the minus D of X, Y, Z in order to apply this inverse transformation. All right, so how do we model like now more complex transformations like the simple model? So if you remember, like what we were doing with the simple model is like consider vertices in a T-pose and applying a series of transformations which were these vertex displacements which were learned from data. And finally, we apply this like blend skinning, as you can see here in the top, which is a linear blend of matrices BI. So this is forward because you start from unposed points and you obtain deformed points at the end. This is a forward mode. However, in implicit surfaces, what we want in reality is like the occupancy of this post space surface. So we cannot start with the canonic space, or at least it's not trivial to do. So what we need to do here is start with the query points in the post space. I want to know the occupancy. And for this, I'm going to have a neural network that predicts these WIs. These are the skinning weights for this point P prime. Now, using the inverse skinning, which is nothing else than taking this linear blend and inverting it, I can obtain P, which is basically these red points, which are unposed to bring them here. And these Ws are predicted with the network FC. BI are known from the simple model. And now this is like one of the key tricks of this paper. Like we want to model these fine-grained details, these changes, for example, like wrinkle deformations or muscle bulging that happen as I articulate the body, which are non-rigid. And instead of having a network that predicts directly the different canonical spaces, which would be hard to learn, what we do is we learn a displacement field in canonic space. So delta P here is basically a function of P in canonic space and the theta, which is the pose. So delta P is actually a three-dimensional displacement field. And now all these red dots have moved to the green dots. And now I can evaluate this SDF, could be an occupancy as well, on this like canonic space after deformation. And this plus delta P is essentially what you could think of it as a continuous post blend shapes. But they, because it's an implicit surface, if you think about it, they work the other way. So basically, if I want to make it, if delta P points inwards, you're making the surface larger, actually. So it's a little bit counterintuitive. All right, and using this model, like we could reconstruct surfaces that look like quite detailed and that have like even complex clothing. It even looks like it's layered, although that's a simple single surface model. And it can be applied to whatever scans you have It could also be like just single garments, or garments with topology that does not follow the body, for example, as shown here. Okay. Yeah, you can check the paper. This model was also trained with a simple data set in order to produce like a simple model that is basically producing implicit surfaces, which would be useful for intersection testing and things like that. So in comparison to another work, which is Scanimate, which basically is conditioning the canonic SDF f of theta on the pose directly, basically this can get better details because it's modeling the non-rigid deformations inside this function, right? So it's basically deforming the points first before evaluating the SDF. And typically doing this, you get better detail. You will see this also when we see the NERF models, like the same trick is applied. Okay. I don't want to spend too much time on this, but basically the conclusions is like comparing to different models. The conclusion was that the model was significantly superior to NASA, and it was very, very much comparable to Scanimate in terms of numbers. Perhaps like neural GIF like can produce better details because of this trick of modeling inside the canonic function. Yeah, you have the numbers here. All right. There are still problems, and you will see. I will explain now what the main problem is. The main problem is that you need to predict for every point in space the skinning weights, and that's a hard learning problem. Like this is illustrated here, and this is like what is illustrated as backward skinning. Backward skinning because for every point in space, in post space, you need to know what the skinning weights are. When the pose is complicated, the skinning field, like this blue and green area, represents the skinning weights learned, okay? When the pose is hard, then you see that, the canonic pose point, which should be here at the edge, is like not predicted correctly, and it's predicted in the middle of the space. That's when the network is not generalizing. And that's because it's hard, right, to learn for all possible poses what the skinning weights are. Instead, in the simple model, when we have forward skinning, that's not a problem. We start with a point and we deform it. And basically the skinning weights in forward skinning are, they would be constant for all this, like as provided that I know the corresponding canonic point X prime. Yeah. So in forward skinning, like this is not varying with pose crazily like here. This is basically more static. And it from this, you can already predict that the learning will be easier if we somehow integrate this forward mode of skinning of the simple model in this learning process. The question is how to do this, and this is non-trivial. So this model, like which is called SNARF, which is called differentiable forward skinning for animating non-rigid neural implicit shapes, it basically learns a canonical shape with this network sigma f, and it learns the skinning weights in the canonic space, not in the post space. It learns the skinning weights, and this is the key, with another network sigma omega, sigma w. And the goal is to learn this network sigma w and sigma f in order to produce these implicit surfaces for unseen poses. Right, so what's the key idea here? Like the key idea is that in forward skinning, you have from canonic space X to post space X prime for all X's. And learning a canonical shape from scans requires to know the inverse. For every X prime, I need to know what the canonical point is. This is what we were solving with inverse skinning. So now in this paper SNARF, what they will do is like given the relationship x maps to x prime, determine the x prime that maps to x, right? And so it's an implicit relationship, but there's no closed form solution. It's a non-bijective mapping because multiple solutions may exist. For a given post point, you might have multiple solutions on the body. All right, so this is the network architecture. And it looks not so complicated, but actually it's more intricate than you might expect. So here we start with this canonic space, x star, and I need to have a network that predicts the skinning weights for this canonic space. This is very similar to how simple works over the surface, but this is defined over the full canonic 3D space. So W here is a vector of weights for that point x star. And now when I pose this point, I need to satisfy that sum of Wi, which are these skinning weights, times the matrices Bi, here's an index missing, x star, should match with the canonic pose point x prime that I'm evaluating, right? And so there might be multiple x stars, x0 until xnb, that satisfy this post point x prime here. For example, in this example, like it shows that the blue dot or the purple dot and the green dot would both pose to x prime. They would both be valid solutions. So you consider all these valid solutions and you obtain the occupancy with sigma f, which models the occupancy in this canonic space. And now, similar to NASA, we obtain the occupancy as the max, right? Which is saying like a point is occupied if it's occupied by any of the parts. This is again. But if you inspect this carefully, x star is not known. You don't know. You only know x prime. You start with x prime, but you don't know x prime, x star. So this requires differentiating through the solution of a nonlinear system. And this is the linear system that you need to solve. And so the question is, how do you do this? So mathematically, you have the following relationship. Find x star such that x prime minus this post point, which is sum over the parts, and the skinning weights, which are predicted by the neural network sigma W, and I indexes the skinning weight of that part. Find x star such that this equation is true. X prime minus the skin point equals 0. Okay? And so the goal here is to find the neural network W weights, the weights of the neural network such that this equation is satisfied and such that this loss that I'm going to define in a second is minimized. All right, so first of all, we have to understand this equation well. This is nothing else than skinning, but now the skinning weights are parameterized with a neural network. And the main difference with backward skinning is that now the skinning weights are predicted in the canonic space, not in the post space, which will be useful for generalization. Now we have a loss here, and the loss is the loss of these neural network parameters, actually also of the parameters of sigma f, but I omitted this here, sigma f being this occupancy network in the canonic space. And so here you have a cross entropy between what? Between our predicted occupancy, which is the max over all these possible canonic points, okay, and the ground truth occupancy at x prime. All right, so go back to this. You take the max of all these predicted occupancies, one for each hypothesis of x0 until xnb, hypothesis of what could be like the canonic point corresponding to this, and then you get the max. All right, so we need to minimize this cross entropy loss. And the challenge here will be to take the derivative of this loss here, this cross entropy, with respect to these neural network parameters. And notice that x star is the solution of this system here, which is a nonlinear equation. And this is what is solved in the paper. If you want to get to the details, you can see how they backpropagate through root finding algorithm. And by doing this forward skinning similar to simple, right? You might get a little bit less nice details. Like the surface might look a little bit smoother, but you can generalize much better to different poses, especially poses that are significantly different from the data set. So you can see here forward versus backward LBS, and backward LBS, as soon as the poses are crazy, it completely breaks down because it doesn't predict the right skinning weights for those poses. All right, so this is a comparison of different methods, and you can see that this forward skinning models, they work much better for difficult poses. Now, in terms of detail, like you lose a little bit, like backward skinning, they're still better. So basically forward skinning models, they have better generalization to unseen poses, but backward skinning models have higher fidelity and are more flexible to model things like loose clothing, for example. All right, this brings me to this final part of this part 2. And all these models that we've seen until now, they are not generative models. And now in part 3, we will see how to make these models generative. I need the ability to, for example, like sample latent code and generate like a full 3D shape model that's an implicit surface. This is what we'll see in part 3. But for this, I will stop this video and I will start a new video. See you in a bit.